In this video, we'll talk about inscribed angles, and we'll talk about some theorems that apply to inscribed angles. So before we start talking about the theorems, let's talk about what inscribed angles are. So the word inscribed means that the vertices of whatever we're talking about are on a circle. So like in the case of an angle, it would look something like this. The vertex is pinned on a circle and then it continues outward. This would be an inscribed angle. Now we could also have, say, an inscribed triangle, and what that would mean is that all three vertices of the triangle would lie on the circle, like so. Or we could have an inscribed quadrilateral, which would mean we have a four-sided figure in which all four vertices lie on the circle. We can do this with any number of polygons. The whole idea of inscribed means that all the vertices are fixed on a circle. So the first theorem we're going to talk about here is very important, very powerful. It's theorem 10.6 in the textbook. It actually has a name. It's called the inscribed angle theorem. That's a very powerful result in mathematics. This is one that I'm not going to require you to prove. Seems to me that it'd be above and beyond what we're expecting you guys to do. But we can use this to prove other things. So it'll be important to understand what it does for us. So the inscribed angle theorem is not too terribly complicated. If I'm looking at this inscribed angle here, so the hypothesis of this theorem would be if angle A is inscribed, then in this case we're looking at angle C is equal to 2 times the measure of angle A. Or, as the case may be, we may see it written like this. Angle A is equal to half of the central angle for that arc, angle C. So the book will try and do its thing where it's talking about the measure of the arc being the measure of this central angle here. I prefer to think of it as terms of angles. If angle A is inscribed, then the central angle for the according arc, then it's going to be twice the size. Okay, now that we have an idea of the inscribed angle theorem, there are a couple theorems that follow directly from it. So, theorem 10.7, this is one that I will be potentially asking you guys to prove. So I'll be thinking as we go through this how you would go about proving it. So if we look at theorem 10.7, in the book it says, if two inscribed angles of a circle intercept at the same arc or congruent arcs, then the angles are congruent. So what that's saying is that if I have two inscribed angles, let's call them angle A and angle B to match the picture, share the endpoints, so let's say arc CB, or CD, rather, then what we're trying to say is that angle B is congruent to angle A. And that is it, meaning that if CD is shared, so both these angles cross through these points, they are inscribed, then I'm trying to say that these angles are indeed congruent. So think about how you would get from starting with the angles being the same, sharing, or not the angles being the same, starting with just this being shared to get to the angles being the same. Theorem 10.8 is another one in the textbook, and it says an inscribed angle of a triangle intercepts a diameter or a semicircle if and only if the angle is a right angle. So really this is just a special case of the inscribed angle theorem. It's talking about what happens when that is 180 degrees. This angle C here, the central angle. It's a diameter, it goes through, well, if we follow the inscribed angle theorem, that has to be 90 degrees. It has to be half the size. So the hypothesis would be if let's say XY is a diameter, then the according inscribed angle, angle Z, has to be 90 degrees. And it's really just a special case of the inscribed angle theorem. The last theorem for this section is theorem 10.9, and it states, if a quadrilateral is inscribed on a circle, then its opposite angles are supplementary. So this kind of ties back to the beginning where we're talking about inscribed can go beyond angles. We can talk about an inscribed triangle, in this case an inscribed quadrilateral, meaning that all four of the vertices are on the circle. So if we have quadrilateral A, B, C, D, and it's inscribed, then what we're trying to say is that these across angles here sum up to 180 degrees. That's what it means to be supplementary. And then likewise with D and B. So I get two parts of the conclusion here. Angle A plus angle C has to equal 180 degrees. And angle D plus angle B has to equal 180 degrees. And that concludes the theorem here. Think about how you'd prove this. Keep in mind that quadrilaterals, all the angles, so if I had angle A plus angle B plus angle C plus angle D, that would have to equal 360 degrees. That'd probably be a useful piece of information to utilize while you're going through this.